The issues about fire in space are, inherently unusual and something you're not going to expect to have seen before. But really, the issue about fire itself is something that, there's aspects of it that you may not be aware of. And so I like to spend a fair amount of time in this talk actually talking about that. And then we'll transition to the latter part and discussing fire in space. I sort of thought of something new. I haven't given a talk like this exactly to this audience before, so I'm trying some different things, so bear with me. And also, I do want it to be interactive, so feel free to stop. I only have like 30 minutes worth of slides, so there's plenty of time for discussion. The first question I wanted to ask, and it may seem a little odd, how many people in the audience drink some type of caffeinated beverage? Okay, keep your hands up, those that do. Now, how many of those in the audience have never had any sort of side effects like a sour stomach or jitters or anything with respect to drinking coffee? How many have never had that type of side effect? Okay, good. So we have about maybe 10% or so. You can put your hands down on those. So 10% have not had side effects, but 90% have. So then I guess the question is, well, if you have those side effects, why are you drinking coffee? Why are you drinking coffee?
Keeps me up.
Okay, good. It gives you energy. So let's just hold on to that. Just remember that thought. That 90% of us drink coffee for energy, even though there's side effects that we'd rather not have. Okay, so that's just sort of a side. We'll come back to that a little bit later, but I wanted to sort of think that through initially. Okay. So now a little bit about fire. So we have, can we turn the lights down a little bit? I think there was, we'll try to get that later. I don't think I can change anything. No. So we've got oh, thank you very much. Picture of a famous actually painting of a woman staring at a flame. And we all know that there's something about staring at a flame that fascinates us. Human beings like to stare at fire. There's something about fire. We can't really put our fingers on it, but we like looking at a fireplace or a campfire or whatever else it is. And this sort of depicts that fascination for fire. So let's talk a little bit about fire, because you don't usually see a cow turn and look at fire, or a horse, or any animal really has any particular interest in fire at all. It's only human beings that seem to have this fascination for fire. So we sort of explore that a little bit more. And what else is there about, for example, human beings and fire? Are there any other unique relationships between human beings and fire? Well, how many civilizations do you think there are that don't have fire, have not in the past, in the entire history? Archaeologists have dug around. How many civilizations, or what percentage of civilizations did not have fire? 0. Good. Every civilization that has ever been discovered, there's evidence that they have fire. So that's sort of an interesting thing. So every human being basically has been affected by fire. You're utilizing fire. What about other mammals? How many other non-human beings use fire? 0. So every human being uses fire, but nothing else on Earth except human beings uses fire. Do we have to use fire?
No.
Why? For food. Good. Why for food? It's a really good answer. I don't know, amazing. That's the first person that really picked that. Why food?
Concentrate on nutrition.
Very good. Very good.
And for shopping.
That's true too. And he said to concentrate on nutrition. So wait a sec. So you're telling me that if I don't have fire, there's a problem?
You have such big brains.
Very good. Wow. Have you read the book making human beings, I think it is. No,
But I will now.
Yeah. The making of human beings. Fire, the making of human beings. I don't go with that book, quite frankly, but there's some interesting facts in it. It turns out that there have been studies done. You say, well, what would you do if you didn't have fire? You just eat raw food. Well, there are raw foodists. Turns out raw foodists tend to have very nutritional food right now because we have the ability to refine things very well that we've never really had in the past. But also often they'll elevate the temperature below boiling, but it's still heating. Oh, we want to put another one on?
This is for the room.
Oh.
So since there's
Oh, got it. So
here,
it's,
if you don't
got
mind.
it. You mean it just makes it louder?
Yes.
Got it.
Hopefully. So thank you.
You're welcome. So I'm all mic'd up.
Is that turned on?
Maybe
yes,
not.
I turned it on.
Doesn't sound, there's something there.
Oh, there we
Okay,
go.
good.
All right.
So there is some heating of the food, but it turns out it's very interesting. If you put someone on a pure raw food diet, there's no cooked food at all, they found that 50% of the women lose their menstrual cycle.
Just gonna,
So what does that tell you about eating raw food?
if we can
It
just
means
get this
that-
on you real quick.
sorry.
I don't think we're hearing you.
Oh, okay, got it. Better?
There we go.
Okay. So it implies that if we did not have cooked food, then we would not necessarily be able to reproduce. That's a big problem. So what does that mean? That means human beings are dependent upon fire. It's not just that we happen to utilize it when it's convenient, but we literally, our entire existence is dependent upon fire. So that's a pretty interesting observation. So that means we've had it for ages, right? Human beings have always effectively used fire. But now we've seen that over time, that dependence, so to speak, relying on fire has grown dramatically. It was a one time for food and for heat, but now it's much more. And that much more really was predicted by this individual. How many of you know about the entropy? I've heard about entropy. And the second law of thermodynamics. So this individual, Carnot, is really accredited with this concept of the second law of thermodynamics, or entropy, which really was all about doing things better, more efficiently. Now, we had the ability to do things a certain way, but until this Carnot came into, his treatise, which is this Reflections on the Motive Power of Heat and on Machines Fitted to Develop That Power, that sort of revolutionized things. Because now we could get, instead of 1% efficient, we're getting 50%, 40% efficient things. So things just dramatically changed when we understood what he taught us. Now, he lived in a time that's very interesting because he lived in a time right around the Industrial Revolution. It was just beginning, right? So he has a frame of mind that's very interesting because we can't not relate to what it was like before the Industrial Revolution. We just have no concept of that. But he did. In fact, he died at, I think, 36 of cholera because he was pre-really Industrial Revolution. We don't die of cholera now, and that's because of the Industrial Revolution. But he was basically in the middle of it, and in fact, helping to create it. And let's look at what he says. Now, this is at the introduction to his famous treatise that really revolutionized science. He says, nature, in providing us with combustibles on all sides, has given us the power to produce, I put this in italics, but the italics is really important to remember, at all times and in all places, that means everywhere and anytime, heat and the impelling power which is the result of it. He doesn't really talk about economics. He's talking about the important things right now that combustibles give us, that fire and combustibles give us, is power everywhere and anywhere at any time. And what does he say about that? That fact seems destined to produce a great revolution in the civilized world. So he's predicting the Industrial Revolution based on the fact that we are able to harness now something that gives us power when we want it and where we want it. Okay? And that makes sense, right? Because to develop a society, we depend on reliable things. When things are reliable, we can do things. When sometimes we have something, sometimes we don't. You know, an unreliable friend, you know, there's problems. Right? As nice a person as they are, if they're unreliable, it's a problem. And society is dependent upon, our modern society is completely dependent upon reliable energy. So he says then, below, it appears that it must someday serve as a universal motor and be substituted for animal power, which economically that's a problem. Waterfalls, which again, even though we think of water as being continuous, it's intermittent because it's dependent upon how is the rain that season. So some seasons we could have a lot of rain, some seasons not. Also air currents. So you know, wind turbines have been around for a very long time, but again, they exist when the wind blows and not when it doesn't. So he says over the first, in other words, animal power is the advantage economy. Over the other two is the inestimable advantage. Notice inestimable, it means we cannot fathom that. Of that it can be used at all times, again, all times and places without interruption. It's a pretty powerful statement. And so we have to sort of try to understand that, right? To really understand what fire has accomplished for humans. Okay. So let's see what happened when this happened, when we harnessed this power. So this is 1824, so this is the time we're talking about. If I can turn the lights on a little bit more, because this is a little bit soft in terms of perfect. This is a very interesting figure. It's a dynamic figure. I'm not going to be able to play it dynamically, but I'll show you motion sort of in segments. But what it's showing is the average lifespan on the y-axis, and it's showing the income. This is on a log axis, so notice this is 400, 4,000, 40,000. And what it's showing is every country has a dot, and the countries are color-coded with the continent that they're associated with. Okay? And the size of the dot represents the population. So there's a lot of information on this figure. Okay? But the main point is, back in 1824, which is really when the Industrial Revolution was just starting to kick in, basically everybody was down in this corner, which means they weren't living very long and they were in poverty. Okay. Everybody. Okay. We, of course, would like to be up here, living a long time and having a decent income. So let's watch what happened. We got to 1910, and all of a sudden, there's some of these countries that are a big yellow, nice big yellow one and a bunch of sort of orangish ones that have pulled out. They're living now 50 years on average. Notice before, the average person actually didn't make it to 40 years old. Now again, there was a lot of this was infant mortality. So some people lived to 80, but many people died at birth or very young. There's child labor, there's all sorts of things that were associated with that. But in 1910, things turned around for this group. And again, this group, it turns out, the orange is Europe, and the yellow is the United States. So Europe, and Britain particularly, were leading the way in the Industrial Revolution, and the United States caught up rather quickly. But what we're seeing is, what happened is, once we got reliable power, then we could have clean water, we could have sanitary conditions, we could have reliable food, reliable heat, those things that keep us alive for a very long time. And we had a manufacturing base that allowed us to increase our income. So all of a sudden, once we've harnessed this fuel, things dramatically changed for those people that had harnessed it. For those people that had not, nothing changed. So what continent do you think is red?
China.
Well, right, and what continent though? It'd be Asia, exactly right. That's right. This is, no, you're right. And this is China. And so red is Asia, and the largest one is China. And the smallest one is, so the second largest one is, would be India. Right. Okay. So then you get to 1945. Notice that we've been accelerating very quickly. We're here. Britain's right behind us. And we're already at 60 years in 1945. Other parts of the world, it's starting to diffuse out. They're developing the ability to have power as well. And so they're growing, but slowly. Blue is Africa. Okay, so why 1945? Why do you think we're living longer? What's the reason we're living longer? I gave some reasons. Any other reasons?
Because we have cleaner stuff.
Good, that's exactly right. We have cleaner stuff. We have clean water. We have clean sanitary conditions. You know, those things that avoid disease. Remember, cholera was the person, Carnot, died of cholera in the 1830s or something because, you know, things weren't sanitary. You know, if you don't have energy all the time, you know, you lose it for a little bit, things get potentially risky. But somebody had mentioned something else, and that was health. Right? Because, yes?
Advances in medical technology.
Medical technology, right. So medicine, right? So that's a question. Was that there because we've improved medicine? So I stopped at this date for a reason. What was the main improvement in medicine that we know of? It was the invention of penicillin. Right, exactly. So penicillin was discovered, I think, in like 1928, began to become effective in 1945. So all the gains we've had here have nothing to do with medicine. It's a real important point to make. We tend to think that we're living longer because of medicine. We are living longer because of medicine to some level. But the majority of the advances are not associated with medicine. They're associated with the ability to have energy at all times and having that power working for us and keeping things going all the time with that reliability that is so essential to survival and to an economy. We keep going, and then we get, notice we're at the 2009, now we're all the way up here. I don't have the movie, but if you show the movie, the trajectory really doesn't change in 1945. So the advances of medicine are incremental improvements to a fundamental change in society. And so now we're able to get from the 75, which is really just having the appropriate water, sanitary conditions, food, and reliability. And then that takes us to the 85 and the 95, where really we have to, you know, make advances in terms of, heart disease and cancer, et cetera, to really be able to live longer lives. Okay. There's another important thing that changed, though. Not only do we live longer lives and have a better economy, but also, and this is a critical component of this, is that the population really took off. So before this is England, and this is the rest of the world. In England, which was really where the Industrial Revolution began, that's when the population started to take off rapidly. So right after the Industrial Revolution, it skyrockets. The rest of the world lagged a little bit. But you can see we're around, 500 or 600 million before the Industrial Revolution. And after that, it took off very rapidly. And now it's in the 7 billion type of level. So why is that important? Because if you really realize, what got us to this point, we were stable at 600 million if we didn't harness combustibles. That's what we could do. That's the amount of food we could have, in terms of just the living, the standard of living, et cetera, was at that level. Now we're at 7 billion. And we're at 7 billion because we've come to utilize the combustibles. Right? So I sort of put this in to make the point a little bit stronger. We've effectively taken off. We're in the air with 7 billion people in a world that really, without combustibles, was at 600 million. And so one thing we have to think about, because there's a lot of goals of saying, that fossil fuels are bad, right? Let's get rid of them. And so the problem is we have to recognize this slide. We are at a state that we are very much reliant on fossil fuels, right? If we jettison the fuel, we don't know what's going to happen. Now, we're doing an experiment right now, and we're not against the experiment. We have to realize what we're doing. We're experimenting because we have no idea whether we can survive without fossil fuels. Right? We know we've gotten here with them. We don't know that we can do it without them. We certainly want to try. But this goes back to why I asked the question at the very beginning. Because one of the things we don't realize when we think about fossil fuels is we only look at one side of the equation. Now, as we look and we say, oh, there's downsides to them. So those 90% of you who put your hands down with caffeine when you saw side effects, then if you would look at that like often we look at fossil fuels, you would never touch caffeine again because you're focusing on the side effects. If you look at it and you say, wow, I didn't realize all this stuff happened. I'm living like a king. I'm living to be 80, and I've got friends and relatives who are living as well, with 7 billion of us. That's an enormous value, right? And by the way, there's downsides too, right? And that's the way we should look at it. And now that doesn't mean we don't try to get off fossil fuels, but we have to recognize the challenges of that, and also recognize the benefit, pros and cons, definitely looking at the cons as they are weighted against the pros. This slide sort of shows how dependent we are on fossil fuels. Right now, this is about 85% of our energy comes from fossil fuels. In terms of combustion, there's about another 5% from combustion of biomass. So about 90% of our energy comes from combusting things. So that's why this talk on fire is, particularly relevant, because our society completely depends upon on combustion, and to a large extent fossil fuels. And I show wind and solar here that are certainly making grounds. And again, I'm not advocating that we don't do wind and solar. I'm 100% for wind and solar. What I'm advocating is when we look at that, we have to recognize that, and I'm going to show this more, that there are always pros and cons to everything, and we have to weigh those two when we're making decisions about what we need to do in the future. So why is it that we have so much trouble? Like what I'm saying right now, I expect most people will say, I've never heard any of this stuff. And it's all new to me, right? So why is that?
All of our information is tainted and picked out of all of it. Like, it's a big bunch of energy, only like parts that will provide profit for the news companies.
Wow, that's powerful. You want to get up here and speak? You got a future. Yeah. I think there is something to that. In other words, we obviously, there is some evilness that we inherently think about in fossil fuels. And quite frankly, I don't fully understand it. I haven't been involved with them a lot and really do very much appreciate what they are. But there's clearly downsides. But part of it, I think, is that we remember in the United States, we see coal miners with black under their faces. We see pictures of trains, the billowing smoke, and we have this image that they're bad. And even though now in St. Louis we get 80% of our energy from coal and we have blue skies, we sort of don't, that doesn't matter. I just remember those things, and I see Beijing, and I see Beijing has pollution, so it must be fossil fuels are associated with pollution, and there's nothing you can do about it. So there's something going on that drives us to really dislike fossil fuels. But I think there's also a lack of understanding of the unique aspect of fossil fuels. Okay? Because we tend to think, well, yeah, okay, there's fossil fuels, but I can get that from something else. So now we have to stop and say, well, what is it that's unique about fossil fuels, and why don't I know that? Okay, so I'm going to try to demonstrate those unique aspects of fossil fuels a little bit in a sort of childish way, perhaps, but at least hopefully it'll bring it home to you in a way that you can hopefully have an image that you won't forget. So here's the question. So you're offered a choice, and so those who are good at math now's your chance to shine. You got 10 $100 bills. I'm going to give you either 10 $100 bills or 1,000,000 pennies. Let's do the math. 10 $100 bills or 1,000,000 pennies.
I'll take the hydrocarbon.
What would you choose? 1,000,000 pennies is 10 times more. That's what we say right now. But I'm going to change the story a little bit. What if the 10 bills were scattered in this room and the 1,000,000 pennies were scattered around Missouri? Now, how many want the pennies? Any? Why? It's the same thing. Right, they're hard to get. Right? They're scattered all over. They're not concentrated. Right? It's just hard to get them. What is the point I'm making? What does fossil fuels have that's very unique? They're plentiful, that's true, but there are many things that, in other words, the pennies scattered all over Missouri, you'd say pennies are plentiful. It's more than plentiful.
We know where to find them.
We know where to find them, right? A little more.
Concentrated.
Good, very good. They're concentrated. We know where to find them. That's a very good point, but also they're concentrated. Just like a $100 bill is a lot of pennies on one little piece of paper. Okay, so really what it is, it's a bird in hand is worth two in the bush. That's sort of what the colloquialism that we would say about that, right? So that's what fossil fuels are. They're basically concentrated solar energy, you know, but they're there, and that concentration is enormous. I'm going to try to point out how concentrated it is by example, but just recall that that's the key point being made here. Another question in understanding energy. How much are these gloves worth? Okay, it's winter time. You're going to the store. Pick one of them and think about how much you would say the gloves are worth to you on a cold winter day.
$5 to $10.
5 to 10. Boy, you're a bargain hunter. I've got to shop with you. Okay, now the next question. How much will you pay for them in June? You're looking for bargains, right? Why? It's the same gloves. You don't necessarily need them, right? But in the winter, you do need them. So the point is, timing is everything. So there's two things that we have to focus on. One is that concentration, and the other one is timing is everything. Okay. Now let's keep that in mind, and we're going to look at a couple different examples. We're going to look at the land area just as an example of something that you can scale and conceptualize. The land area needed to produce a relatively small amount of energy. This is 5 megawatts continuously. That's what it takes to power the student campus housing at Washington University, about 5 megawatts. It doesn't need it all the time, but sometimes it needs it, particularly in the middle of the summer. And so we're going to see how much land use does it take to do that if I get it from different sources. So I'm going to look at a coal, and I'll look at wind, and we'll look at solar. Okay, so if it's coal, I need to burn it in something. So I'm down here, if you can see, I hope you can see this in back. Here's a little power plant, not particularly important, but just to describe that. You recognize this is Forest Park. So we're going to use Forest Park to be able to produce enough power for the dormitories at WashU. Okay, now this thing in red here, this is the seam that I would have to excavate to get the coal to be able to do that. And that's on a year, for 1 year. Now notice what I've picked here is ideal conditions. So this is a very thick seam, so I don't have to really do too much work because it's very thick. I'm going to show the very best wind and the very best solar also. So this is an example, if I have the best resources, which you only have those for a little bit, you have to deal with the best and the not so best in life, and so that's the same thing here. But right now we're going to deal with the best, and then we'll look at the average. Okay, so this is for what it takes every year, and every year you'd have to do that. So if you 20 years, you'd have excavated this, but then presumably then you would seed that area, and then gradually you just keep going through the process. But this is what it takes for a year. Okay, let's see what it takes for solar. So this is solar. It says 5 megawatts. Now why is it so big? There's two reasons. One of them is because
So the sun can hit it to power.
That's right. The sun's going to hit it and power it. But if I just had this little spot here, the sun would hit that. It just isn't going to give enough power for that dormitory. Dormitory is pretty big. The kids live there. They like to, have their electricity on, and their air conditioning, their heat, their take showers, things like that. So they need it. They need more than just what you can get from this. So you need to build this whole area to give it to them, so they have it all the time.
The fossil fuel, that's a year's worth of fossil fuel in that small area. So that amount of area right there would be maybe like 50 years.
That's right. It's very good.
Those would live until they're destroyed.
Right, that's exactly right. That's right.
So
Yeah.
however long you want to take care of them.
That's true. I mean, they would have a lifetime, but they would live a long time. Exactly right. But realize that when you're looking at that this is nothing else grows here. In other words, you've affected things. So that's what we're trying to do right now is you affected the land there. It's no longer a park. And so you have that power, but you have that power at a cost. But a very good point. In other words, you have to deal with the fact that this system can sit there, and that's why I tried to point out that this region is only for 1 year.
After you take out that entire seam, and then let's say 10 of them, do you put dirt back?
That's right.
Because you would have to, I mean, that would obviously have to be very deep, and that looks pretty large.
Yeah, so that's
You
it.
have to put the dirt back, and you would already affect that area too.
That's right.
And you'd have to regrow the trees.
Exactly right. So what you're saying is 100% true. And this is what they do. They will mine this seam, move the dirt off of it, and then put it back. They won't do it in this strip like that, but that's the idea. They'll mine a section, take the dirt off, and then put the dirt back on. It's sort of like what you do when you're building a house. You move the dirt off, put in the foundation, then you move the dirt back. But what you're saying is exactly right. So let's keep going. And now let's take a look at wind. Okay, so wind is a different situation. Whereas solar, you basically no longer have anything growing. You've destroyed the ecosystem below this system. But here you have not. You've got a system that is basically still growing grass, and you can have trees and the like. So this has really not had a major effect on the land use that you have. But this, again, is ideal conditions. So now let's go take a look and see what happens if we're not ideal. This is just average. So now we have average conditions. And again, we have our plant. I've expanded the scale. Just so you know, this is the region that we're powering, that area right there. So just get a sense for what it takes to power that region. And this, again, is the land use that would be on a yearly basis. So again, you have to continue to do this every year. And this is solar. So about a quarter of Forest Park. Now notice that this land, this is the region, is powering this region here. Now you've probably seen, you say, this doesn't seem right. And what I'm pointing out here is the timing is everything issue as well. In other words, there's a density of the energy, the concentration, that makes it big. But what we have to do here is we have to supply it all the time. So what this plot is showing, it's coming from the National Renewable Energy Laboratory's site. It's telling you if you have to have it all the time. So then you have to have additional panels to make sure that when the sun's not shining, you have it stored in batteries. So this is assuming you have continuous. Okay? And often when we look at wind or solar, we don't look at it as supplying it all the time. We just look at it as happy to have it when we have it. So this is changing that dynamic to say, what if I need it all the time? And then wind goes like the cube of the power of the velocity of the wind, so it's quite a bit larger. And so again, this is not to say that we don't do wind and solar. We 100% need to. But what we have to recognize is that this is the trade-off. We have one thing that this young gentleman said very wisely, is we're disrupting that land for a period of time, and we have to go back and be good, Samaritans and reseed it and put it back to where we found it. But there's challenges with it. There's environmental challenges even outside of the extraction that we have to deal with. But we recognize there's trade-offs. We have one that is relatively concentrated and continuous, another one that is rather low density and not continuous. This gives you an example of the size that we're talking about as well. We don't realize the size of the wind turbine. This is a Vesta wind turbine that is 2 megawatts. So one of these wind turbines, if you take a typical power plant that's maybe a gigawatt plant, it would take 2,000 to 3,000 of these wind turbines, so about 2,000 to 3,000 arches for a single power plant. And again, it's because of that high density as well as the intermittency. And this is what's really, is happening. It's in fact just what I was showing as a diagram is in fact really what's happening today. So again, this is not a bad thing in certain communities, but right now there is pushback. There's pushback from the rural countries want their, so to speak, countryside back. So it's not a panacea necessarily that we can, we can't guarantee that, this is going to be accepted continuously in the future. So now shifting away from that, just recognizing that we don't have a simple solution to getting rid of fossil fuels. So now what does that mean? So, what do we do? Because we obviously have issues associated with fossil fuels. We have local issues, but we recognize the United States has done a very good job of cleaning up the air associated with fossil fuels. But we still have CO2, so we have to deal with the CO2 as well, and that's something we really haven't dealt with. So this is a wedge that sort of, a system is called a stabilizing wedge. How do we control the amount of CO2 that we're putting in the atmosphere? And to do this and to get down to where we'd like to be, which is down here, we have a lot of things we have to do. We have to have renewables. We have to have efficiency. We have to have improved vehicle efficiencies. This one over here is the one I want to talk about. It's geological disposal. It's that concept of carbon capture and sequestration, where you capture the CO2 and put it underground. Okay? So that's part of the wedge. Everything needs to be done. And I think we all have to just try, work as hard as we can on all factors to be able to address these issues. But certainly one of them is this, and that's what I'd like to be able to describe. And then what I'm going to do is to show some experiments in space that are associated with enabling that to happen. So this is the idea behind carbon capture and sequestration. This would be a power plant. And the idea behind that is you capture the CO2. Normally the CO2 would go out of the stack and just in the atmosphere. You took the coal or the whatever you're burning from underground, and so now the idea is to return the CO2 to the same place or close to the same place as you got the fuel. And so here you take the CO2, it's a pure stream of CO2 that's sent underground, and then it's in some region underground that it can store for effectively indefinitely. And then you have power without CO2. Basically, it's effectively near zero emission power. But the difference here is that this power now is a type of power that comes when you want it and where you want it. And this is an example of how that's done. So here's a typical boiler that would be, you'd see in a, oops, let me try a different pointer. This one's running out of juice. And what you do in a typical boiler, it's not that much different than, say, a candle. Where you take a fuel and you put in air and they burn, and then you have tubes where there's hot water, and the hot water generates steam that spins a turbine, and that turbine produces electricity, and then you get electricity. Here though, they want to have pure CO2 at the outlet. And air has mainly nitrogen, right? It's almost 80% nitrogen. So you don't want to put nitrogen underground, you just want to put CO2 underground. Nitrogen it doesn't really have any effect on the atmosphere. So what you do is you get rid of the nitrogen by taking it out of the oxygen, out of the air. So you just all you want is the oxygen. So simple chemistry, O2 plus carbon makes CO2. C plus O2 makes CO2. So we just want to have the O2 because it's the energy of making CO2 that is really what is powering what fossil fuels and biomass have in terms of being able to produce energy. It's producing CO2. So what happens now is they take that oxygen, there's a little bit of science to things, and out of this we said is pure CO2. Now has anybody ever seen an oxyacetylene torch? You can cut through metal with that thing. Oxygen and acetylene, when you get rid of the nitrogen, it's really high concentration, things get very hot. So you've got to dilute this system somehow to keep it from burning up. So if you took the nitrogen out of the oxygen, you put something back in to dilute it, and what they do is they take the CO2 and put it back in. Okay? So you can take the oxygen and put the CO2 back in. And then it becomes like air, but instead of having nitrogen as a diluent, it's CO2. So that's the principle behind this thing. Okay. So this I'm sort of showing that concept. So here's, say, some fuel. You take oxygen, you take the CO2, and you produce heat. And basically you end up with CO2 and water. Okay, now this is the issue that we've been studying, and that is, again, this is for those, it's relatively straightforward chemistry. If you have questions, stop me, but you should be able to, I believe, understand these concepts. It's not that, not going to get too detailed. So say you have a fuel, and then this is air, okay? So you have, it comes with oxygen and nitrogen. Okay. And then you end up with products. Okay. So the interesting thing is, if you take this nitrogen, it comes with the air normally because that's how air is. It's got oxygen and nitrogen in it. But if I've already got a system now that only, I've removed the nitrogen, now I have pure oxygen. Now I have a choice. I can take the inert and put it back in with the oxygen, or I can put it back in with the fuel. Right? I can do either one. If I put the nitrogen, or we'll say the inert, back in with the oxygen, then it's this type of system. I have the fuel burning with this mixture of oxygen and a diluent. But I could just take the diluent and put it with the fuel. So now I have diluted fuel burning in pure oxygen. It's basically the same temperature, so the basic system is very similar. Okay. So now the question is, what do? Do I put the inert, when I'm going back to this system, when I have this flue gas that's going to dilute something, do I put this flue gas back in with the oxygen, or do I put it with the fuel? That's the question that we would raise. Okay, both of them have the same flame temperature, regardless of what we do. So they will behave similar, at least in terms of getting the heat out that we want. Okay, in walks soot. Okay, so soot is a byproduct of combustion. You've seen in the back of a bus or a truck, this black stuff, it's basically effectively nearly pure carbon that's unburned. And so it's coming out of the exhaust. It turns out this is a flickering, so to speak, candle. Does anybody know what the yellow is? We think it's a flame. It turns out it's really not the flame. It's a flame because we call it the flame. But from a scientific perspective, it's really not the flame. Turns out what this is, and I'm going to show this in a minute, it's actually soot that's emitting light. So you have like your stove top, if you have electric stove top or your oven, and you turn it really hot, you see that there was black elements, but when they get hot, they start to glow. They can glow orange. Well, if you got them even hotter, they start to glow yellow. So if you think about, you go back to these particles are black particles, just like your element. But when they get very hot, they emit light. It's emission, just like emission from the sun. So this yellow that you're seeing are those black soot particles that have been heated up till they're glowing out yellow. Okay. Okay, I want to sort of show that. If I can, maybe I think I can just light this. It's just a candle. So I've got a candle, and now what I have is just a piece of glass tube. Now what happens when you have hot particles and a cold surface, there's a phenomenon called thermophoresis. And what that does is when there's a particle that's hot and it sees a cold surface, it's actually attracted to the cold surface. Okay? If this was hotter than the particles, then they would move away from it. But since this is colder than the particles will gravitate towards the surface. So what I'm going to be able to do is I'm going to put this thing into the flame, and the particles in the flame will deposit onto this thing, and they'll quenched, and so then you'll be able to see them. So you're not going to be able to, can we turn on the lights for just a second? So what I've done is I'm just putting the quartz into the flame, and then it comes out black. Right? So it's just these particles are just basically deposited on this black surface. Okay. Now why are they not, if I go over here, they don't deposit, right? There's nothing deposit, I don't see any black smoke, why not? What? Well, but they're not existent, right? I mean, they're not, they're consumed. Very good, exactly right. In other words, these hot particles are seeing air, so they're burning up. And that's why I said before, that's not the flame. that's just the indication of these particles. The flame is there. We can't see the flame because it's covered up by the particles. The particles are so bright that we can't really see the blue flame that's buried beneath them. Okay, so this is, we sort of understand sort of what soot is, but it's not a good thing, right? At least it's not a good thing when it comes out of an exhaust system. Okay. So we'd like to be able to have the ability to regulate this. Here's an example of it in sort of an extreme. You get what's happening here is you've got fuel that's really being cooked by all this heat and producing an enormous amount of soot coming out of the back end of that. And this is what it sort of looks like when you look under a microscope. It's a major pollutant, responsible for many deaths annually in the U.S. But it turns out that actually in the power plant it can be beneficial. It can radiate heat to the wall. So it has pros and cons. Depending if you have it where you want it, you just don't want to have it where you don't want it. So dealing with soot is a big challenge. And so we want to try to understand that. Now I want to step aside for a minute and step back and discuss a little bit about different types of combustion. Okay? Because what I've showed right here is a type of combustion where, for example, if I take this system, this is our propane torch. I'm going to modify it a little bit. Okay? What I'm doing is normally in a propane torch, you see these little holes? So if I take this off, there's basically this is pressurized gas. It's a liquid fuel that has a certain vapor pressure, so it's under pressure. And there's a little bitty hole in the tip of there. And when I open this valve, the gas shoots out of that hole. Well, anybody that's studied fluid flow knows that when you have a high velocity, that leads to a low pressure. Okay? So when I have that high velocity jet, it means right at that jet the pressure is very low. It's called Bernoulli's equation. So, So what does that mean? So it means when I take something like this and I turn this on and I have holes in that, what's going to happen if it's low pressure? The air is going to go inside. Right? So when the air goes inside, it's going to mix with the fuel. It mixes with the fuel. When it comes out to here, it's a mixture of fuel and air. Is that what I had when I did this? Very different system. I had a wick. There's no air. Where'd the air come from? From the surroundings. Very good. So the air is coming to the fuel by way of the surroundings. Here, the air and the fuel are mixing, and then they're burning. Okay? So what I'm going to do first is I'm going to put this on here. I'm going to cover up the holes. You've never seen this necessarily because you always burn these things where the holes are, right? But I'm going to just cover up the holes. Okay. So you have what looks very similar to a candle flame, right? Okay, and notice that it goes up. Why does it go up? Heat rises. Well, why doesn't it? Maybe I'm pointing up, though. Can it be I'm just pointing up? Could be. What do I do to experiment to find out? Point down. Okay. So sure enough, I point down, it still goes up. So you're very good. It's less dense. So does that mean it will always go up? If it's less dense, why not? What's that? Okay, good. But can I do something to make this thing not go up?
Make it denser than air. Make it, denser than air.
Okay.
So denser than basically nothing.
Yeah, so you could, if you could make it denser than air, it wouldn't go up. And you're right. And the reason it goes up is because the temperature makes the density go down, right? I mean, go up. It doesn't go down. So when I have a high temperature, I have a low density. So it's like a cork. It's lower density in the water. The cork goes up. So the gas, when it's hot, is lower density than the surrounding, so it goes up just like the cork. But notice the following. I'm going to now pull this thing off. Now the system completely changed. Now it's not going up. Right? Not only that, it doesn't have any soot in it. Right? So it's a very different flame. Just do it again. Where the air is coming from completely changes the dynamic. Now this system that I'm showing you right here is the system that like a diesel engine works on. It's a spray of a liquid fuel. So it burns like this. And notice what's it producing? Soot. So we said that the candle had a good feature where there was a lot of soot in it, but it all burned out before it left. Right? But if you don't get everything right, it doesn't always burn out. Right? In fact, when we stuck this thing into it, we see a lot of it didn't burn out. So depending on what you do, it could be fully consumed. Sometimes it isn't. Anybody remember a story in the news that's very associated with diesel engines and emissions?
Yeah.
Right, this scandal with Volkswagen. Exactly right. So Volkswagen was trying to deal with this. It's a challenge to get that exactly right. You want high performance, it makes it very hard to avoid those emissions. Right? Because you can have incomplete combustion, you end up with things like that. So it'd be nice to be able to have a system that was like this, that doesn't produce soot. But not all fuels work that well in this type of system. Diesel fuels don't work that well this way. But there are fuels that do. For example, gasoline. Gasoline can actually evaporate and mix. So in our engines and our cars, our petroleum where we're using regular gasoline, they burn in more like this mode. So you don't see a lot of soot in those cars because they're basically burning very clean like that. Okay. But there's a lot of applications. Most of industry is like this. Most of nature fires are like this, where they're basically a fuel on the one side and an oxidizer on the other side, and they meet at the flame. Okay, that's how the system works. But that leads to soot and other pollutants. So the question is now, we have this system where we said that we have the ability to, going back to here, oops, sorry, wrong way. We have the ability to put the inert either with the oxygen or with the fuel. So from the perspective of capturing CO2, it doesn't matter. But from the perspective of soot, it could matter. So let's see what happens. Actually, I'm going to set aside and break and talk about microgravity for a minute before we see what happens, just sort of introduce this. So we want to see what happens when we change the amount of inert, where the inert is, whether it's with the fuel or the oxidizer. That's our question. But we're going to find that the way we're going to answer that question is actually it depends upon microgravity. And I'll explain why that is in a minute. First, I want to just talk about microgravity and what it does to a flame. So this is a picture of our candle. And as we pointed out, see the blue? That's where really the oxidation, the fuel and oxygen are actually burning together. So if you follow that contour, where does it end up? Right about there, if you just extrapolate the curve, right? What's happening right there? Very good, because why? Because that's where the flame is. So when you look at a candle and you see that point right there, you see that's where the flame is. That's where the oxidation processes occur in the fuel and the oxidizer. But there's a bunch of particles in there. And as you pointed out, the particles are going to see oxygen. They're hot, and hot environment with oxygen, they're going to burn. So what you're seeing up here is not the flame, it's just the soot particles burning up. And when you get to this tip, you notice that they completely burned up because basically there's nothing left. You have the ability to burn them up. If you take a candle that's got a very long wick, it doesn't have the ability to completely burn them up, and then you'll see soot shooting out the tip. But if the candle's appropriately constructed, that doesn't happen. Now there's another fascinating thing. This is a birthday candle. Now remember, just so as an aside, we're talking about the uniqueness of fire. There are many different things that are very unusual about the relationship between fire and man.
Fire and what?
Man, human beings. So one of those is, we just got done talking about what does fuel consume? Oxygen. What does it release after it's done consuming oxygen? You know, what do human beings consume? And what do they emit? So very interesting, isn't it? They actually, same relationship. Another very interesting, I hope you don't mind me getting a little bit, I don't know what you do, sentimental or something like that. But there's another interesting aspect of fire that if you think about the soot is one of the best absorbers known to man. This is what we actually have for our printers. It's effectively soot. It's modified a little bit, but effectively soot because it's black and it can absorb light. So this is an interesting concept. So the soot basically is absorbing. So from a philosophical perspective, soot sort of takes. Right? But what does the fire do? Exactly right. It takes something that intrinsically, at its nature, is to take. Right? But what it ends up doing is it illuminates. Right? So interesting thing, because it's sort of a perspective on life. Right? What are we doing here? You know, we can take what we have and be a taker, or we can illuminate and give. Right? And so the fire has that same characteristic. It's intrinsically taking something that would be a taker and converting it into something that would be a giver. Now, why am I saying that? Because remember, there's something going on in our minds when we see fire. Right? We don't understand what it is, but we have some connection to fire. Right? And so you start to look at these things and you realize there's aspects of fire that are very connected to human beings that are subtle. Right? What's another one? Well, if I take a leaf and I blow on it, it just blows away. If I'm in a river and a leaf falls on the river, it floats down the river. But if I'm in a river and all of a sudden I get knocked off and I'm flowing down the river, I start swimming hard. Right? The leaf just goes down the river, but the human being or the mammal is going to fight very hard to swim upstream. Right? It has that nature to it. Why do I say that? Well, if I blew on that candle, then why doesn't it just blow away? It doesn't do that. Next time you light a candle and blow on it, you will notice that the characteristics of that candle are to survive. It doesn't survive in any way the same way we do. But the harder you blow, you see it's hard to blow out a candle. Why? It should just blow away just like a leaf. But what happens is the dynamics of a candle, when you start to understand fire, it has characteristics associated that it strengthens itself when it's trying to be put out. Just like we will fight hard if that current is trying to take us downstream, we will learn and get energy that we never thought we could. And so the fire actually has a similar type of dynamic that's completely unrelated to any type of biological thing. It's a strictly biological system, right? But it has this characteristic that, again, has something unique that's similar to the characteristics of, so to speak, survival that, is one of the fundamental characteristics of human beings. Okay, so let's take this fire and let's take it out of a buoyant atmosphere. And let's get rid of gravity. The reason it rises is just like a cork rises, because if there's a difference in density, then you'll get the lower one, the more dense will go down, the less dense will go up. And so that's what's happening right now. The flow is driving the fluid up, and so that's making it this type of candle shape. You get rid of that in microgravity, there's no preference to go up or down. This is the wick, the fuel's coming off of the wick, and then oxygen is diffusing in. So there's no motion here of bulk fluid motion. It's just the process of what's called diffusion, and the fuel and the oxidizer come together and meet. So you get a completely different structure. And so there's a lot of different studies that are done in the space station or in microgravity conditions, where the goal is to say, wait a second, we got to put astronauts out in space. They got to be safe. We could potentially have fires. We have to understand the physics of that. So a lot of the work that's done on the space station is literally to try to make sure we understand what's going to happen. Sometimes you have a situation where, in fact, something that would be combustible on Earth is not combustible in space. In space, I don't mean when you're outside the space station, but inside the station, because of course it still needs oxygen. So there is no fire, so to speak, in space when there's no oxygen, but there is fire in space when it's inside the space station, and you're supplying it with oxygen. But you're not giving it gravity. So now its behavior changes, and you have to understand that. At the same time, there are situations where you can have something that wouldn't be combustible normally on Earth, and in fact it is combustible in space. So you need to know both of those things, when it is and when it isn't, and how that differ from space if we're going to have safe space travel. Okay. And I think I'm running short on time, so I'm going to tell you about a YouTube site that I'd like to show you some neat ones. And if people want to stay over, I'll play that. But I'm going to keep moving on just to get to the key sort of point that I want to make. And I'll let you know about this YouTube site if you're interested, where you can see all sorts of interesting pictures of fire in space. But here's the issue. Where there is a desire to understand what happens with respect to fire in space, for safety reasons, etc., it also turns out that the space station is an experimental station. So it allows you to do experiments that you can't do on Earth. Okay? And it's unique in that way. So there's different reasons we go to the space station to study fire. So obviously we need to study it for safety, but I'm going to talk about a different one. I'm going to talk about where you say to yourself, I need that characteristic of no gravity to be able to prove the point or find out this thing that I really need to find out. Okay? And so now we're going back to the carbon capture and sequestration. That issue about where do I put the inert if I want to control soot? Okay, that's the question. And we got to answer that question. Okay? So we had a theory. And our theory said that there's some fundamental characteristics about the properties of the flame that are affected by that process. Okay? And so what we wanted to do, let me step back for a minute. What we wanted to do is to prove that point. Because what happened was, on Earth, when we changed where the inert was, we changed where the fluid was flowing. Okay? So imagine right here, if I have this system, these soot particles are going into the oxidizer right here, right? They're shooting into the oxidizer, so they're burning up. Right? So if I'm trying to say, look, if you put the inert with the fuel at the same temperature, you're not going to produce soot, which was our theory. Or you put it with the air, and you will produce soot just like this, then that's a big finding, right? Because you're able to eliminate soot. But if when you do that, you're changing the direction of the flow, what we were doing is you couldn't decipher. Is it because we changed the direction of flow and put the soot into the oxygen? Or was it fundamentally a characteristic of the dynamics? Now, I can't get into exactly what the characteristics of dynamics are, but it's associated with just the structure that exists when you have it in one case or the other case. So what we did is we said, well, okay, let's go to space where we don't have gravity, because gravity was the problem. Gravity kept pushing the flame the way we didn't want it to go. So we couldn't decipher that on Earth. Okay? But once we had gravity, we could develop a different type of experiment. So this is the idea. We wanted to separate out the fact that the direction of the flow could take the soot into the oxidizer and, of course, burn it up, versus the fundamental characteristics of putting it in one versus the other. So now we have a system. We have a perfectly one-dimensional flame. It's a spherical flame. We can't do that on Earth because, again, buoyancy would always lift the flame up. But what we can do now is we call it normal structure, which is our typical sooty flame, or the inverted structure, which we consider the flame that should not produce soot at all. Okay? In this case, our normal structure takes the fuel, which is where the soot's going to form, right, where there's fuel, and brings it into the oxidizer. Right? So that's basically, you could have soot here, but it's going to burn out just like our candle. The soot goes into the oxidizer. In the inverted structure, we predict that you shouldn't have any soot at all. But, you know, what you're doing is you're taking, if they show this way, you know, maybe it's because the soot's just oxidizing because you're sending it into the oxidizer. Then you go down to a different approach, and this is what we can benefit from microgravity. Instead of having the fuel on the inside and the oxidizer on the outside, we reverse it. We have the oxygen on the inside and the fuel on the outside. Now, when soot forms here on the fuel side, it goes straight into the fuel. So any soot that would be formed into this fuel, the direction of the flow is pushing it, and it's happy just sitting there. Nothing happens to it. Remember this one, when I produced the fuel, there's a flame sitting here, and it burned it up. Okay, so we have these different dynamics. Now this situation is the key question. Because this one was going from a fuel to an oxidizer. That's going to burn things up. But this one is going, when you have the soot forming, it's going outside into the fuel. I'm sorry you really can't see this. There's supposed to be a flame here. You can barely make it out. But this would be where you would have the soot formed, and it would go into the oxidizer. So if it's due to the fact that there's some fundamental characteristic, this flame should be blue. If it's due to the fact that the direction of flow is taking the soot into more fuel, it should be sooty. Okay? So that's the study we had to do. We had to go to microgravity to be able to answer that question. This is the system. It's just a spherical system with a flame around it. And so remember, this one is we're going from the fuel to the oxidizer, so it's going to be, soot's going to basically burn up. And so that's what we have. This is a spherical flame, and you can see there's some soot in there, but it burns up. There's oxygen out here, so the soot never leaves there. Then we have this flame. Oops. This is our inverted flame that we predicted would not form any soot, and it doesn't. But again, it's not conclusive because the direction is from the fuel to the oxidizer. So it could be that somehow we've formed it and burned it up real quickly. Okay. And that's what we sort of were able to show on Earth. This one is the one we expect to be very sooty because its structure, this is on the side of standard air fuel type of flame, says it should form soot, and the soot's going into more fuel, so the soot's just happy to continue to survive. Right? And then this is the last one. So theoretically, if it's based on velocity going, it should be sooty. If it's based on structure, it should be clean. I didn't know that was going to show. Well, mine, I wasn't going to have that on. I switched computers at the last minute. And okay, so whatever. So drum roll. So it worked. Anyway, so that's all I had to say. There is a good YouTube. If you go to YouTube and you look at microgravity flames, there's some really fascinating flames. Flames in space, a lot of different things can happen, and there's continuing studies and finding more all the time. There's a study right now that we're actually involved in as well that is looking at, there's some chemistry associated with combustion that we never even realized existed. It's called cool flame chemistry. It's really like cool flame, but not because it's neat, but because it's low temperature. And so there's things that we're learning in space about combustion all the time. I'll take any questions?
So you can eliminate the soot. Does this have any other practical applications yet?
In terms of this type of studies?
Yes.
Yeah, there are. One of the things that is, from a practical perspective, when you're dealing with carbon capture and sequestration, you have a choice of where you want to put it. Where are you going to put the inert? You're taking CO2 out. You can put the CO2 with the fuel or with the oxidizer. So we have a program right now where we're looking at carbon capture sequestration, and where we put the inert is driven by these type of studies. Because we really want to produce. It turns out in a power plant, you want to produce soot because it radiates, but you don't want to produce too much because then it goes out the stack. So this ability to control exactly how much you want, and we're using these concepts to do that. But there's also in terms of material synthesis. So when you're doing something like this, sometimes you want to synthesize materials in a flame. It's a well-known application of combustion. Our tires right now are really produced from combustion-generated soot. So we actually, it's like the carbon black. The soot is effectively carbon black, and that's what goes into tires to make them last for 40 or 50,000 miles, is that strong carbon. And so the ability to synthesize materials in flames is established industrial technologies, and this type of approach allows us to tailor the synthesis to produce different materials. Any other questions? I know I've said some controversial things here. Does anybody want to challenge?
The coal has a lot of heavy metals in it. Mm-hmm. How is modern coal technology addressing the mercury and the other contaminants?
Yeah, so what you're saying is exactly right. There's a number of metals in coal, and one of the particular one is mercury. There are methods of eliminating it, but there aren't a lot of regulations on eliminating it. So there is actually, what you're using to eliminate it is activated carbon. So it's something like soot. It's a little bit different. But it's effectively a carbon-based sorbent that you can pass the flue gas through and it absorbs the mercury. So that's the technology to eliminate it. But right now, there's not a requirement to it. Some power plants do it, but it has not been required of all power plants at this point.
So I think in a space station, they actually don't experience that much less gravity than we're right now. They're just sort of falling with the space station around Earth. That's why like they don't experience that much gravity as we do.
What do you mean they don't? You mean they have low gravity?
Yeah, lower gravity than we have right now, but they still experience a lot of gravity. But the reason why they don't experience it is because they're sort of falling with the space station around the Earth.
That's right.
Which we can have a similar effect if we just have like a plane that goes up and dive into a free fall. Which means, do you think we can do a similar kind of experiment in that kind of a plane that have the same effect as in a space station?
No, it's very, very observant and very, very well put. What you're saying, everything you're saying is very, very appropriate and true, and they do. So many of these experiments are done before they go to the space station. You go through a rigorous effort to go through these planes. Another perspective, you know, when you're in an elevator and the elevator comes to a certain floor and then stops, what you're doing effectively is you're experiencing low G for a little bit, and your stomach sort of goes up. Why does your stomach go up? Because basically you've lost gravity for a moment, and your stomach is sort of sitting there. So it's the same idea. They'll take your experiment in, say, an 8-story building, and they drop it. And so during that period when it's dropping, from its frame of reference, there's no gravity. And so they're able to simulate microgravity in those type of experiments. Same as a plane, but in this case, it's a little bit higher quality gravity because really there's nothing touching them. When you get really good quality, they get put under a vacuum, so there's not even any resistance, and then it gets almost, you know, very close to 0 G.
Yes, going back to the solar panels and the wind versus the wind. And you said something about the environment and the impact. It was kind of hard to hear you at that time.
Okay.
Can you explain that a little bit more? Is that not a good alternative based on environment? I'm thinking about the wind is an interruption, bird migration, things like that as well.
Well, I think you're right. I mean, I'm not suggesting that that wind and solar aren't very good things to do. I'm just explaining that there are consequences to everything we do. And so we have to make a judgment. So like you're saying, you know, bird migration is an issue. You know, eagles are killed by wind farms, and solar as well, because imagine you know, a bird flying over a hot environment like that, particularly concentrated solar collectors can be very high intensity energy. So there are issues in terms of using wind and solar, but you know, they've got many positives. So they really, when it comes down to it, if you think about this intermittency, we'll get into a little bit of the details of this. If I have this massive infrastructure where 80% of my energy is from systems where I can get you the power when you want it, so that's the way the system is right now. All the systems are designed, other than wind and solar and to some extent hydro, they have the energy there, and when you need it, when you turn on your light, believe it or not, every time we do that, it triggers an exact match between what you just required and what's supplied to the power plant. It's an exact match. It's not like it's close. It's just dead on within, you know, a couple of zeros type of thing. So it's very close to being a perfect match. So and we require that. If we didn't have that, our frequency would vary and things would start to go a bit haywire. So that match means that the system works well, because if something changes, we just put more fuel in, and that deals with that match. That's how the system's stabilized right now. But we don't know when, you know, if there's people all of a sudden come in, it's a hot day, you know, and the air conditionings all come on. We just have to put more fuel in to supply that. And so that dynamic is dealt with. But when you have, your supply, you can't know what it's going to do, then you have a mismatch of that. You all of a sudden want to demand power, but it's not there. So when you are basically a small percentage of the grid, that's not a major problem, because if you go away, it's just as if the demand went up. So then the fossil and the nuclear will kick in, and the hydro will kick in to be able to balance that. But when you get to be, say, 50%, you don't have that dynamic anymore. And so this is where the challenge comes. So in other words, at least from my perspective, going full bore towards wind and solar makes a lot of sense. Recognize there's going to be people that are going to resist it. It's not going to go without any detractors. But that's only going to go to a certain point. The real challenge is going to come when we start to have large penetration. Germany is an example of this. Germany went really heavily into wind and solar. In recent years, they've backed away. Germany is unique in that it can sell its power to the rest of Europe, and it can buy, France has nuclear power, it can buy power when it doesn't have power. So it has the ability, so to speak, to sell and buy, to regulate that to some level, but it only works to a certain level because that dynamic gets challenging. Even though there's somebody wants to get it to you, there's not a electric line that can take it there. They're fully, they're only rated for so much current, and if you're past that current, if you need more, you're not going to get it from that source. So there's that balance becomes challenging as you put more and more sources of energy that aren't power when you want it. And so that is really where we start to say, even though I would be very much in favor of wind and solar as much as we can, we have to have other things in place that are not polluting that can address the shortcomings of wind and solar.
About the wind and solar hurting the environment, wouldn't the power plants for fossil fuel be first off killing all the trees and plants that you need to dig up and all the other animals that live in there, and then all the heat from the power plant and all that soot killing any bird near it by effectively covering it in carbon, weighing it down, and possibly weakening it, same for all other animals that would fly there. And that would spread over, it would weaken obviously as it spread, not as concentrated, but it would still affect everything, which is why they're basically knowingly letting thousands of people die each year in America and not doing anything about it. Because that's still hurting the environment about as much as just cutting an eagle in half.
Okay, right. And I think your point is the critical point. I think it's very well said. In other words, one thing you have to realize, and this is why I showed the land use issue, because let me ask a question. How many people really have seen a power plant? Okay. How many people have seen wind farms? Okay, right. So we have, comparable, have seen both, right? But wind is about 5%, and the rest is 80 to 90%. So the point is that we have a substantial amount of land use. So what you're saying is true, that we locally, we have a source of pollutants. Locally we do. It's just they're not as scattered. So the amount of them is much less. So when you're dealing with this, you have to deal with trade-offs. And so what you're saying is correct. If I had a power plant like used to be in China's power plants were very dirty, they've cleaned them up a lot, you have major impact on society. You have a responsibility to make them clean, right? And so we have to make those systems so they don't do what you're saying they would do. And we've shown that we can do that. It costs money and it takes effort, but we can do that. But we have other things, it's not 100% good, right? There's negative aspects associated with it as well. And so what you're addressing is correct. There are negative aspects associated with fossil fuels. And there's negative aspects associated with wind and solar. And that's the whole point. It's not that there's one is good and one is bad. They're both sources of energy, both have their pros and cons. We have to do our best to clean them all up. Right? But the problem is we can't walk away from here and think we can get rid of fossil fuels and do that because it's not going to have any negative impact on society. That would be a mistake. And we don't want to go down that path because it's too dangerous. Our society, the beginning talk is, our society is fully dependent upon this. The best way to kill people is turn off the electricity. And if you look at the blackouts, that's where you have a major challenge in terms of sustaining life. So we have to be very much moving towards what you're saying, clean source of energy, but doing it in a way that recognizes the challenges that we have in doing that honestly.
Going back to Forest Park, how much area of pitch blende would have to be mined to make 5 megawatts of power in 5 days?
Yeah, so this average seam, I have to think about that. It's in the same neighborhood because this was average coal, average seam.
Well, it takes about the same amount of area for uranium.
Oh, you're talking about for uranium?
Pitch blende, yeah.
Oh, pitch. I'm sorry. I thought you were talking about pitch from a carbon perspective.
No.
Yeah, no, it'd be much less.
Even smaller.
Yeah, it'd be much smaller.
You should get a pretty big bang for your buck.
Yeah, exactly. Nuclear is a completely different story.
So, like, if you, like, mine, like, all the coal and oil, even if you, like, reuse it and stuff, would there, like, small amounts of it leaking out, like, eventually destroy, like, the atmosphere? And would it, like, it mean that, like, slowly switching to oil, hydro, and solar power would be more better since it would be, like, not destroying the atmosphere over the course of hundreds of years?
Yeah, so I think what you have to look at, you have to say, well, what are those things that are a problem, and can I address them? So you're correct. You have to look at those challenges and say, can I address them? So what I'm showing here is a technology that wouldn't have those emissions. So you look at the old technologies and they do. So you don't want to look at the technology and say, well, the old technologies cause these problems, so we can't deal with that source of fuel. We have to ask the question, if we cannot clean them up, if there was no way to get rid of CO2 in a power plant, then we've got a problem. But if there are ways to get rid of CO2 in a power plant, or soot, or mercury, then we have to look at that because it has that intrinsic benefit that basically gives us power when we need it. Okay,
last
sorry.
question.
Okay,
Then, yeah.
last question.
Yeah, I think the guy, yeah.
I was going to ask, what do you think is the most exciting new combustion technology that's coming out?
Well, there's I would say in terms of the carbon capture, there are technologies. I'll tell you what's. Can I just take 2 minutes? It'll take a 2 minute, couple minutes to explain this. One of the challenges of this technology that we talked about in terms of the combustion, where effectively you don't have a smokestack. You know, everything's going underground, and you're basically putting pure CO2 underground. So that means you could have power that was very clean power, and it's reliable. So what's the problem? It's expensive. Okay. So I'll give you a little perspective on new technologies that are coming out, because it sounds great, but it's too expensive. It's a problem, and it's particularly a problem because it's a global issue, CO2. It's not a local issue. So if we can't get every society to buy into this, then we've got a problem. So if we have something that's costing enormously, or it's not a reliable source of energy, then it's a problem because we're not really giving people what they want. So we have to get the price down, and we have to get the emissions down. And so one of the things that happens, if you look at a power plant, we've all seen the power plants, you see pictures of them, they see that white plume coming out, and sometimes they'll show it looks like it's pollution just billowing out of the power plant. How many people think that that white cloud is pollution billowing out of the power plant? It's water vapor, right? Because we said that the carbon and hydrogen, the hydrogen in the fossil into the fuel makes water, and there's actually water in coal as well. So there's a lot of water coming out of the stack. So if I take my stove top and I put a kettle on it, and I turn the gas on and I'm burning this stuff to make steam, I get the same type of thing. I get steam coming out of there. What did I do to make the steam? I put a bunch of energy into the thing. So that steam coming out of the power plant is wasted energy, right? You never think about that, right? But that's a bunch. You had mentioned, there's a heat coming out of the power plant. That steam coming out of the power plant is just wasted energy. It's doing nothing. It's warming up the atmosphere. But it turns out that if you can run the system under pressure, like a pressure cooker, the temperatures are higher in a pressure cooker. So that means if you get that steam in a pressurized system, then that steam condenses. Okay, and when it condenses, it releases back that heat that it took to make it. So all of a sudden now you are able to pressurize the system and get that heat back that you were wasting right now. So why is that good? Because remember, we're trying to reduce the cost. So if we make the process more efficient, then it doesn't cost as much. Now why don't we just do that right now? Well, the problem is right now we don't want pressure because then we're going to just unpressurize the system. So you don't want to pressurize the system and then unpressurize it to put out the atmosphere. But when you have carbon capture, you're putting it underground. You actually have to put it underground under pressure. The pressure is like 100 bar. So it's very pressurized. So you're going to pressurize it anyway. So that means if you're going to pressurize it anyway, you can pressurize the combustion process. And all of a sudden the price drops down considerably. So now you're starting to bridge that gap. So imagine if you could go out to China or go out to India, go out to Africa, and tell them, look, you can have reliable energy with low emissions, clean skies, and even no CO2, and at a price that's comparable to what you're paying now. So if you can start to do that, then people aren't going to say, well, I don't know about this stuff. I'm not worried about it, or I am worried about it. You don't have that debate anymore. You've got the opportunity to give people a locally clean environment, which people care about, and a globally clean environment as well that some are going to be concerned about. We're concerned about. We're a wealthy nation. But Africa, you can't expect them to be concerned about it, nor India, or even China for that matter. So we have to come up with solutions that are incremental increases in costs that are, people will say, I'll buy into that. And so I think those type of technologies will allow us to have the power that we need reliably in a low polluting type of mode, and hopefully we can get there.